This is a recast of the 6,200-word piece, Policy Gradient Networks, from cumulative.com. This article provides an overview of policy gradient networks in the field of reinforcement learning. It explains how these networks optimize the parameters of a policy network to learn optimal policies and handle environments with continuous action spaces. The article discusses their applications in robotics, game playing, and natural language processing, as well as their advantages and limitations. It also covers topics such as activation functions, convergence and optimization methods, and the role of reward functions in policy gradient networks. Overall, policy gradient networks hold great promise for advancing the field of reinforcement learning and enabling intelligent decision-making in complex environments. Let's listen in.
Today we're diving into the world of reinforcement learning and specifically policy gradient networks. These networks have been making waves in the field of machine learning, particularly in training agents to perform complex tasks.
Absolutely, Theo. Policy gradient algorithms are a popular approach in reinforcement learning. They use gradient ascent to optimize the parameters of a policy network. And let me remind our listeners that policy gradient networks are a type of machine learning model used in reinforcement learning tasks.
That's right, Samantha. Unlike value-based methods that estimate the value of each state action pair, policy gradient networks directly learn a probability distribution over possible actions given an input state.
Exactly. And the key to policy gradient networks is their ability to learn the optimal policy by iteratively improving their actions over time. They achieve this by leveraging the concept of policy gradients, which is a technique used to update the network's parameters based on the gradient of the expected return with respect to the network's parameters.
And this is significant because policy gradient networks can handle environments with continuous action spaces, whereas some other methods struggle with such complexity. These networks have been successfully applied to various tasks, such as robotics and game playing.
Absolutely. Policy gradient networks are of crucial importance in the field of reinforcement learning due to their ability to optimize models and learn from real-world experiences. They have proven relevant in various applications, such as robotics, game playing, and natural language processing.
And one interesting aspect is that policy gradient networks continuously update their parameters based on the feedback received from the environment. This enables agents to perform tasks more efficiently and cope with complex and dynamic environments.
That's right, Theo, and I think it's worth mentioning that policy gradient networks have been enhanced by incorporating baseline techniques. These techniques reduce variance and provide unbiased gradient estimates, thereby improving the overall performance of the networks.
Absolutely. The implementation of policy gradient networks has shown promising results in various domains, including reinforcement learning tasks. They offer a unique approach to solving the exploration-exploitation problem by directly optimizing the policy without requiring a value function.
And by leveraging the power of deep learning, these networks can handle more nuanced and refined policies. This means they can adapt and learn from diverse datasets, making them a valuable tool in artificial intelligence research.
Definitely. Now let's briefly touch on policy gradient methods in general. These methods have gained significant attention as a viable approach for training neural networks to perform complex tasks.
That's right, Theo. The main idea behind policy gradient methods is to optimize the policy directly, allowing the network to find the best actions in a given environment. This is achieved by estimating the gradient of the policy's performance with respect to its parameters.
And by using gradient ascent, these methods update the network's parameters in a way that maximizes the expected return. They leverage the concept of the objective function, also known as a performance measure, to guide the optimization process.
And this adaptation of neural networks to various environments enables them to learn more sophisticated behaviors. It's an exciting area of research with great potential for advancements in reinforcement learning.
Absolutely, Samantha. Now, let's take a step back and briefly explain what reinforcement learning is for our listeners who may not be familiar with it.
Reinforcement learning, or RL for short, is a subfield of machine learning that deals with decision-making in uncertain and dynamic environments. Unlike supervised learning or unsupervised learning, RL focuses on learning optimal decision-making strategies through a trial and error process.
That's right. In reinforcement learning, an agent interacts with an environment and receives feedback in the form of rewards or punishments based on its actions. The agent's goal is to learn a policy that maximizes the cumulative reward over time.
And to do that, our L algorithms make use of value functions, which estimate the expected rewards of being in a certain state or taking a certain action. These value functions are continuously updated based on the observed rewards, allowing the algorithms to make better decisions over time.
And that brings us to the end of our discussion on policy gradient networks and their role in reinforcement learning.
Indeed, Theo. We hope this overview has shed some light on the inner workings and potential advancements in this exciting field.
Absolutely, Samantha. One key difference between policy gradient methods and other approaches in reinforcement learning is that policy gradient methods directly optimize the policy, while other approaches often involve value function estimation as an intermediate step. This direct optimization allows policy gradient methods to handle large action spaces more efficiently.
That's right, Theo. Another advantage of policy gradient methods is that they can learn stochastic policies, which means they can explore and potentially perform better in uncertain environments. This flexibility in controlling agent behavior is a significant advantage over other reinforcement learning algorithms.
However, it's important to note that policy gradient methods also have their disadvantages. One major drawback is their high variance, which makes them sensitive to initial conditions and requires careful tuning of hyperparameters. This can make the convergence of these methods slow, as they need to explore the entire action space.
That's a good point, Theo. Another approach to solving the credit assignment problem in reinforcement learning is through the use of policy gradient methods. These methods employ a neural network called the policy network to approximate the policy function. By iteratively updating the parameters of this network using gradient descent, the algorithm learns to maximize the expected reward over time.
Absolutely, Samantha. And it's worth mentioning that policy gradient methods have been found to be effective in a variety of reinforcement learning tasks, including game playing and robotic control. However, they do have some limitations, such as being sensitive to hyperparameters and having high variance in the estimated gradients.
That's true, Theo. Now let's talk about the components of policy gradient networks. These networks consist of several interconnected elements that work together to facilitate efficient learning. Firstly, the policy network is at the core of these networks and is responsible for making decisions based on input data and generating corresponding actions.
Alongside the policy network, another key component is the value network, which estimates the expected cumulative reward for a given state or action. This estimation helps guide the learning process and improve decision-making.
Absolutely, Theo. And the eligibility trace is another vital element of policy gradient networks. It computes the gradient update based on the current state, action, and obtained reward. This trace helps to update the parameters of the policy network effectively.
That's right, Samantha. And finally, the baseline network provides a reference value for comparison while evaluating the performance of the policy network. This comparison helps determine how well the policy network is performing and guides further optimization.
Now, let's talk about the architecture and design of the policy network. One important aspect is the choice of activation functions. These functions determine the outputs of each neuron in the network and capture the nonlinear relationships between inputs and outputs.
Absolutely, Samantha. Commonly used activation functions include the sigmoid function, the hyperbolic tangent function, and the rectified linear unit function. The choice of activation function can significantly impact the performance of the policy network and should be carefully considered.
That's right, Theo. Additionally, the number of layers and neurons in the network, as well as the type of connections between them, should be carefully considered to strike a balance between model complexity and computational efficiency.
And to wrap it up, policy network models have emerged as a powerful approach for tackling a wide range of important problems in reinforcement learning. Through policy gradients and stochastic optimization techniques, these networks can effectively learn policies that maximize long-term cumulative reward.
Absolutely, Theo. And while there are limitations and challenges associated with this approach, it's evident that policy network models hold great promise for addressing complex decision-making problems in various domains.
That's right, Samantha. One of the key elements in policy network models are the activation functions used in shaping the output of each neuron within the network. These activation functions, such as sigmoid, hyperbolic tangent, and LU, play a crucial role in mapping input values to a desired range and setting negative inputs to zero.
Absolutely. And the choice of layer types used in policy networks depends on the specific architecture. For example, convolutional layers are commonly used for processing visual inputs, recurrent layers are suitable for sequential data, and fully connected layers are employed to process high-level representations and make final decisions.
Yes, and in terms of improving the architectures of policy network models, researchers have introduced variants and enhancements. One such approach is the use of recurrent neural networks, RNNs, such as long short-term memory, LSTM, which have shown promising results in capturing temporal dependencies in sequential decision-making tasks.
Another improvement is the incorporation of attention mechanisms, which allow the model to selectively focus on relevant parts of the input. This has been particularly useful in complex environments with high-dimensional observations, as it allows the model to attend to important features and ignore irrelevant ones.
These variants and improvements have led to more accurate and efficient policy gradient methods, enabling agents to adapt over time and handle complex decision-making tasks effectively.
Absolutely. Now, let's move on to the role of the reward function in policy gradient networks. The reward function is a crucial aspect of reinforcement learning and policy gradient networks. It determines the goal or objective in a reinforcement learning scenario and provides feedback to guide the learning process.
That's right. The reward function quantifies the quality of a state or action and influences the network's learning process by assigning higher or lower values to different actions or states. Through this guidance, the network learns to maximize its reward and improve its policy accordingly.
The reward function can be designed based on the specific requirements of the task at hand, taking into account factors such as task completion, efficiency, or even fairness. Its accurate formulation and design are vital for the success and effectiveness of policy gradient networks.
Designing reward functions for specific tasks is a crucial aspect of policy gradient networks. The choice of a reward function directly impacts the learning process since it determines the objective being maximized. In complex tasks, defining an appropriate reward function can be challenging.
Absolutely. The designer needs to consider the task requirements and specify a reward function that aligns with the desired behavior while avoiding potential pitfalls, such as reward hacking. It's also important to strike a balance between being informative enough to guide learning and being scalable for larger tasks.
And there are challenges and limitations in defining reward functions. Sometimes the desired outcome or behavior is not easily quantifiable, making it difficult to determine what rewards should be assigned to different actions. Additionally, reward functions can be subjective and influenced by societal or cultural biases, leading to rewards that may not accurately reflect the true value of an action.
That's right. Determining the proper scale for rewards can also be problematic, as there might not be a clear linear relationship between actions and rewards. These challenges highlight the complexity involved in designing effective reinforcement learning agents.
Despite these challenges, policy gradient networks have emerged as a powerful tool for efficiently training complex reinforcement learning agents. They enable direct optimization of a policy's parameters by using the gradient of the expected return with respect to these parameters.
And by parameterizing the policy as a neural network, policy gradient methods can scale to high-dimensional input spaces and handle continuous action spaces. Moreover, the policy gradient algorithm can handle both deterministic and stochastic policies, making it flexible and adaptable for various applications.
Absolutely, Samantha. With further advancements and research efforts, policy gradient networks hold immense potential in advancing the field of reinforcement learning and enabling intelligent decision-making in complex environments. One of the key challenges in training policy gradient networks is finding the right balance between exploration and exploitation. Exploration refers to trying out different actions to gather more information about the environment and potentially discover better solutions. Exploitation involves using the learned policies to maximize rewards. Finding the optimal balance is crucial because excessive exploration can lead to slow convergence and inefficient use of training samples, while excessive exploitation can result in suboptimal policies.
That's right, Theo. The article suggests that techniques such as epsilon-greedy policies or Boltzmann exploration can be used to balance exploration and exploitation. In the epsilon-greedy approach, a certain percentage of the time the agent explores random actions, while the rest of the time it follows the current best strategy. The Boltzmann exploration assigns probabilities to each action based on their expected rewards. These techniques help ensure a balanced and effective learning process.
Absolutely, Samantha. Another important aspect to consider when utilizing policy gradient networks is convergence and optimization methods. The goal is to efficiently find the optimal policy that maximizes the expected return. One popular approach is stochastic gradient ascent, where the policy parameters are updated in the direction of the gradient of the objective function. However, directly computing the gradient can be computationally expensive, especially for complex environments.
That's where optimization techniques like natural gradient methods and trust region methods come into play. These methods seek to balance exploration and exploitation while enabling efficient and effective convergence to the optimal policy. They help address the computational complexity issue and make training policy gradient networks more feasible.
Definitely, Samantha. Now let's talk about some applications and case studies of policy gradient networks. In robotics, these networks have been successfully applied to tasks such as grasping, locomotion, and object manipulation. They can learn complex behaviors from raw sensory input, which has also made them excel in autonomous driving.
That's right, Theo. Policy gradient networks have also been employed in natural language processing for tasks like text generation and dialogue systems. They have shown promising results in various domains, firmly establishing them as a powerful tool for solving a wide range of real-world problems.
Absolutely, Samantha. And let's not forget about game playing. Game playing has long been utilized as a testbed for developing and evaluating machine learning algorithms. Policy gradient networks have emerged as efficient tools for training game-playing agents using gradient-based methods. By optimizing the parameters of a policy network through gradient ascent, these networks can learn to make decisions that maximize long-term rewards in a game environment.
That's right, Theo. The use of policy gradient networks has not only provided significant improvements in the playing strength of agents, but has also demonstrated their ability to adapt and learn from experience. This makes them invaluable tools in the field of game playing and beyond.
Absolutely, Samantha. It's clear that policy gradient networks have the potential to revolutionize the field of reinforcement learning and enable intelligent decision-making in various domains. One of the main advantages of policy gradient networks is their ability to learn complex strategies and optimize policies through continuous training. This has been demonstrated in various domains, such as board games and video games. For example, AlphaGo Zero utilized policy gradient networks to become the world champion in the game of Go. This showcases the remarkable capabilities of these networks in enhancing game performance.
That's right, Theo. Policy gradient networks have also been successfully applied to specific games like Atari 2600 games and Dota 2. A3C, which stands for Asynchronous Advantage Actor Critic, was implemented in Atari 2600 games and achieved state-of-the-art results. The OpenAI 5, a team of AI agents trained using proximal policy optimization, PPO, exhibited exceptional performance in the complex game of Dota 2. These examples highlight the potential of policy gradient networks in improving game performance.
Absolutely, Samantha. Policy gradient networks have gained significant attention in the field of deep reinforcement learning. One of their advantages is that they have the ability to learn and optimize policies directly without relying on a value function. This offers several advantages over traditional value-based methods, including greater stability and improved ease of implementation. These networks have been successfully applied to a wide range of tasks, such as autonomous driving and robotic control.
However, it's important to note that policy gradient networks also have certain limitations. They can be prone to instability and slow convergence, requiring extensive training and careful hyperparameter tuning. Additionally, they struggle with high-dimensional state spaces and suffer from the curse of dimensionality. Despite these limitations, continued research and advancements in policy gradient networks hold promising potential for future developments in game playing.
That's right, Samantha. Now let's shift our focus to the field of robotics. Robotics involves designing and constructing physical machines capable of interacting with their environment and performing tasks on their own. Combining artificial intelligence and robotics allows researchers to develop robots that can navigate complex environments and accomplish tasks that are too dangerous or labor-intensive for humans.
Policy gradient networks also show great potential in the field of robotic control. Traditional methods for controlling robots often involve manually designing control strategies based on rules and heuristics. However, these methods fall short in complex and dynamic environments where robots need to adapt and learn from their experiences. Policy gradient networks enable robots to learn control policies directly from raw sensory inputs, allowing them to adapt their behavior in real time based on the current state of the environment.
Absolutely, Samantha. However, there are real-world challenges and considerations when using policy gradient networks for robotics. One of these challenges is the requirement of an adequate exploration strategy. In order for the policy gradient network to effectively learn the optimal policy, it needs to explore a variety of actions in different states. However, exploration in robotics can be challenging due to high-dimensional continuous action spaces and potential risks associated with physical interaction with the environment. Careful exploration strategies, such as adding noise to the action selection process, need to be employed to ensure effective learning.
Another important technique used in policy gradient networks is the use of a baseline. The baseline acts as a measure of the expected return against which the actual return is compared. By subtracting the baseline from the actual return, the variance can be reduced. The choice of baseline is important as it affects the bias of the network. Different baselines can be used, such as the average return or a learned value function. The inclusion of a baseline helps in stabilizing the learning process by reducing the fluctuation of gradients used to update the network's parameters.
That's a great point, Samantha. The use of a baseline is crucial in improving the stability and convergence of policy gradient networks.
Absolutely, Theo. Policy gradient networks have shown remarkable successes in game-playing tasks and offer several advantages over traditional value-based methods. However, they also come with limitations and challenges, especially when applied to real-world robotics. Nevertheless, continued research and advancements in policy gradient networks hold promising potential for future developments in game-playing in the field of reinforcement learning.
Definitely, Samantha. One area where policy gradient networks have gained considerable attention is in natural language generation. These networks optimize the parameters of deep neural networks to generate coherent and meaningful text that adheres to a given set of guidelines or rules.
That's right, Theo. By using policy gradient networks, researchers have been able to improve the quality and accuracy of generated text in tasks such as machine translation, dialogue systems, and summarization. This has made significant strides in the field of natural language generation.
However, there are challenges and opportunities in using policy gradient networks in natural language processing. One challenge lies in training these networks, as they require a substantial amount of data to effectively optimize their parameters. The non-deterministic nature of policy gradient algorithms can also lead to unstable training processes.
Absolutely, Theo. But despite these challenges, policy gradient networks offer several opportunities in NLP applications, such as dialogue systems and machine translation. They can optimize sequence-level objectives directly, resulting in coherent and contextually relevant responses in dialogue systems. They've also shown promising results in improving translation accuracy by modeling the target sentence generation process.
Exactly, Samantha. The challenges and opportunities associated with policy gradient networks in NLP highlight the potential for advancements in natural language understanding and generation. It's an exciting area of research with a lot of room for growth.
Moving on to reinforcement learning, policy gradient networks have gained attention for their ability to address high-dimensional and continuous state spaces. They utilize deep neural networks to approximate the policy function, learning complex and non-linear mappings between states and actions.
That's right, Samantha. By utilizing gradient-based optimization methods, such as stochastic gradient descent, policy gradient networks can estimate the gradient of the policy function and update the network's parameters accordingly. This allows them to learn policies that maximize expected rewards, making them a powerful tool for solving a wide range of reinforcement learning problems.
Absolutely, Theo. And looking towards the future, there are several areas for advancements in policy gradient networks. Firstly, there is a need for more efficient and sample-efficient algorithms to alleviate the high variance issue inherent in policy gradient methods.
Yes, and incorporating curricular learning and transfer learning techniques into policy gradient networks can enhance their ability to generalize across different tasks and environments. This could lead to more robust and versatile networks.
Additionally, exploring the use of hierarchical policy gradient networks can enable the learning of complex behaviors and decision-making processes. This could open up new possibilities in solving reinforcement learning problems.
And lastly, investigating the integration of external memory mechanisms or attention mechanisms into policy gradient networks can improve their ability to handle long-term dependencies. This could be particularly useful in tasks that require remembering past information.
Absolutely, Theo. These future directions and advancements hold great potential for further enhancing the capabilities and performance of policy gradient networks in reinforcement learning tasks.
And it's worth mentioning that improvements in policy gradient networks have contributed to advancements in reinforcement learning algorithms as a whole. Techniques such as trust region policy optimization and proximal policy optimization have been introduced to address issues like sample efficiency and convergence.
That's right, Theo, and methods like generalized advantage estimation, GAE, have been employed to better estimate future rewards. The combination of policy gradient networks with deep neural networks has also allowed for the handling of high-dimensional, complex problems, leading to substantial improvements in performance and applicability.
Absolutely, Samantha. These advancements in policy gradient networks have had a significant impact on reinforcement learning algorithms overall, making them more effective and versatile in solving a wide range of problems. One interesting development in the field is the incorporation of neuroevolutionary algorithms within policy gradient networks. Neuroevolution uses genetic algorithms to evolve neural networks, operating on the principles of Darwinian evolution. By integrating these algorithms, policy gradient networks can potentially optimize complex systems more efficiently.
That's right. Neuroevolutionary algorithms can enhance the ability of policy gradient networks to learn and optimize policies in challenging real-world problems. By leveraging the strengths of both neuroevolution and policy gradient methods, this integration offers a powerful framework for training agents and tackling complex tasks.
And speaking of policy gradient networks, these networks have gained significant attention in deep reinforcement learning. They directly optimize the policy function, allowing agents to navigate complex and high-dimensional action spaces effectively.
That's correct. Policy gradient networks use gradient ascent during training to improve the policy parameters iteratively. By estimating the expected return through sampling and taking the gradient of the expected return with respect to the policy parameters, the network can update its policy in a way that increases the expected return.
Exactly. This approach offers advantages over value-based methods, such as simplicity in handling continuous action spaces and the ability to converge to locally optimal solutions. However, there are still challenges that policy gradient networks face, such as high variance and the risk of getting stuck in suboptimal policies.
That's a great point, Theo. Despite their advantages, policy gradient networks still have room for improvement. One challenge they face is sample inefficiency, which refers to the need for a large number of samples to achieve good performance. Another challenge is the lack of theoretical guarantees, which hampers the understanding and predictability of these networks.
Absolutely, Samantha. To fully unleash the potential of policy gradient networks in real-world applications, further research and development are needed. These challenges must be addressed to ensure that policy gradient networks can achieve their full capabilities.
In conclusion, policy gradient networks have emerged as a promising approach in reinforcement learning. By directly optimizing the policy function, they provide a flexible and effective way to train agents in complex decision-making tasks.
That's right. These networks have been applied successfully in various domains, including robotics, game playing, and autonomous driving. They offer solutions for controlling robotic agents and training AI models.
However, there are still challenges to overcome. Sample inefficiency and the lack of theoretical guarantees need to be addressed for widespread adoption and effectiveness of policy gradient networks.
Exactly, Samantha. Continued research and development in this field hold promising potential for advancing the field of reinforcement learning and artificial intelligence. With further advancements and improvements, policy gradient networks have the potential to revolutionize multiple industries and drive innovation in the near future.
Well said, Theo.